Hello students. Today we will discuss two topics concerned with the fourth module, that is a short electric dipole and thin linear antenna here. So usually this linear antenna can be considered as consisting of a large number of very short conductors here, which are connected in series here. And a short linear conductor is called a short dipole, and it is of a finite length here. So let us consider a short dipole as shown in the particular figure here. You can see this particular figure. Here we are having a short electric dipole here, which is of a length L here, through which the current I is being flowing here, and the whatever the width of this particular dipole is there, it is small d here, and there is a transmission line that has been connected exactly at the center of the dipole here. There are two end plates here. This is end plate 1 and end plate 2 here. Now, what is exactly the idea of this short dipole here? Now, according to this particular short electric dipole here, the length L is very short here. Okay, this length is very short compared to whatever the wavelength of operating is there here. That is, L should be less than, very less than lambda here, and the plates at the end of the dipole provide capacity loading here. See, you can see this particular end plates here, which has been attached at the two ends of the dipole here. Those provide the capacity loading here. Okay, the short length and the plates result in what you can say that uniform current here. Okay, uniform current of I here along the entire length L of the dipole here. Okay, remember, and whatever the diameter we are having here, or the thickness we can say, or the width of this particular dipole is very less compared to the length of the dipole here. And so you can see the same thing in the particular figure here. The dipole may be energized here. Okay, how exactly this dipole is been energized with the help of a transmission line here. Okay, this transmission line does not radiate here, and the radiation from the end plates is considered to be the negligible here. Okay, so fun figure what B here, what you can see here is thin conductor is there here of length L with a uniform current of I here, and there are point charges that is been there at the ends here, plus Q and minus Q here. So you know the current and the charge relationship here. There is current and the charge relationship correlated by dq by dt is equal to capital I here. Now, what we are exactly interested in here is what are the fields that are related to the short electric dipole here. Okay, so the fields of a short electric dipole here. Now, let us consider a dipole of length L here, which is placed along the z axis here and perpendicular to the y-axis and the x-axis here. Okay, now whose length is capital L here, and here the phi is nothing but here your azimuth angle here, which is in this particular direction. Theta is nothing but here your polar angle here. There is a point P at a distance R here, okay, through which these three fields are being going out here. That is electric field here in the direction R, and E theta and E phi here. Now consider whatever the medium is there, and the dipole is assumed to be air or vacuum here. Okay, now look into this particular figure here, figure B here. So what exactly you're going to find here is you're going to consider a small element of this particular short dipole here, that is delta z here. Okay, so now which is been considered from the distance of z here from the origin here. Okay, and now there is a point P here, which is the far field here, which is the far. Okay, from this particular point P, we are trying to get the electric field here from this particular short length of dz here. Okay, now from this end of this particular dipole here, S1 and S2 are the distances we can consider here. If at all we consider dz as a small elemental here, from there if you calculate the distance, it is S here. Or if you try to calculate the distance here from the origin here, or you can say that the middle of the short dipole, it is R here. Okay, now this particular whatever the short dipole is there here. Okay, if it is making an angle of theta here with respect to what you can say that with respect to this center of the origin, the point P here. Okay, now what we are interested is we wanted to find out the relationship between the electric field components ER, E theta and E phi here. Okay, now if we consider that the current is flowing in the short dipole here, and the effect of the current which is at the point P here is not felt instantaneously. That means it is not felt immediately here. So, but after an interval equal to the time required for the disturbance to propagate over the distance r here, this is known as retardation effect here. Okay, so now one there is a retardation effect is not considered here. The current I will be given I is equal to I naught e raised to j omega here, which implies that instantaneous propagation of the effect of the current here. Okay, now if at all we consider the retardation effect here, then there is a change in this particular equation here. Square bracket, okay, I is equal to I naught e raised to j omega into bracket of t minus of r divided by c square bracket here. Then this is, let us consider this equation as equation number 2 here, where square bracket I is considered as a retarded current and the c is nothing but here velocity of propagation here. Since we need to consider the retarded potentials here for a dipole here, so the retarded vector potential of electric current has only one component here in this particular case here, that is in the direction of z here. So that's why az will be considered here. Okay, so what is exactly the value of az here? Az is equal to mu naught divided by 4 pi minus L by 2 plus L by 2, okay, into bracket of I divided by S dz here, where I is nothing but here, square bracket I is nothing but here retarded current, and it is given by I is equal to I naught e raised to j omega t minus f s divided by c here. Z is nothing but here distance to a point on the conduction here, distance to a point on the conduction here, and there is nothing but here. This is the distance. Z is distance on the point of conduction. That is dz. You can consider here. Okay. Now I naught is nothing but here peak value in time of current here, and mu is nothing but here permeability of a free space here, that is 4 pi into 10 raised to minus 7 and the per meter square here. Now, if at all we consider that the distance from the dipole is very large compared to the its length here, and also compared to the wavelength here, then we can say that S is equal to R here. And neglect whatever the phase differences of the field contributions are there in different parts of the wire here. So in that case here, what we can say that we can just modify or reduce the equation here to what Az is equal to mu naught L I naught e raised to j omega t minus part 0 by c divided by 4 pi r here. The retarded scalar potential V of a charge distribution is V is equal to 1 divided by 4 pi mu naught, okay, into integration of V to rho divided by S into d tau here. Now, where rho is nothing but here your retarded charge density here. Thus, retarded charge density is given by rho naught is equal to e raised to j omega t minus of s divided by c. D tau is nothing but here infinitesimally small volume element here. Okay. So epsilon naught is nothing but here, you know, the permittivity or the electric constant of a free space here 8.85 into 10 raised to minus 12 farad per meter here. Since the region of charge is confined at the end of the dipole here. Okay, so whatever the charge we are going to consider here, right? So this particular charge has been confined to the only the ends here, plus q and minus q here. It has not been related to the other structure of this particular wire here. At the ends of the short dipole, we are able to find the charge here, plus q and minus q here. If that is the case here, so what exactly the meaning here is? Now the region of the charge is confined at the ends of the dipole here. Then we can, as shown in the particular figure here, we can reduce this particular whatever the retarded scalar potential is there to what it is. V is equal to 1 over 4 pi epsilon into flower bracket of square bracket q divided by s1 minus q divided by s2 here. So this is nothing but equation number 6 here. Now we already know that the relationship between the charge and the current here, dq by dt is equal to I here. Let us take this denominator term and dt into this RHS here. So if at all we have the integration kind of a thing, then we have this particular thing, this I naught e raised to j omega t divided by s by t here and dt here. And if at all we try to integrate it, you will be having square bracket of I, okay, retarded current here you can consider divided by j omega here. There. Now substituting the equation number 7, whatever we have just got it, and 6 here we have substituting 7 in 6 here. What exactly we are having? We are having this equation number 8 here. What is exactly this equation number 8? It is scalar potential here. Okay, retarded scalar potential. Now, what we are going to consider here is, if at all we consider the distance r should be much more greater than the length of the particular dipole here, then whatever the lines are there here, okay, okay, so whatever lines connecting the ends of the dipole, this is the end of the dipole, and this is the end of the dipole here, which are connecting the ends of a dipole, and the point P can be considered as a parallels. In that case, S1 and S2 have been written as S1 is equal to R minus of Elliot by 2 cos theta, R plus of Elliot by cos theta here. Now, substituting this equation number 9 in 8 here, we have the fields for short electric dipole here. Electric fields of short dipole ER is equal to I naught L cos theta e raised to j omega t minus of r by c into bracket of 1 divided by cr square plus j omega r cube here. And e theta is equal to I naught L sin theta e raised to j omega t minus of r divided by c j omega c square r plus 1 divided by c r square plus 1 divided by j omega r cube here. Okay, so now we got the electric fields of a short dipole in the direction of r and theta here. We don't have any kind of an electric fields in the direction of phi here. That is nothing but azimuth parallel here. So this is how we can understand regarding the short electric dipole here. Remember here, first and foremost thing, we have to draw this particular diagram here. Explanation concerned with this particular diagram we have to mention here. Then we have to draw this particular diagram so that where exactly a short dipole has been placed, we have to understand. And then from where a small elemental element is set, we are going to calculate the fields here, fields of a short dipole here. Okay, now with this thing we have to consider the retardation effect here. Okay, retardation effect, with retardation effect the current has to be found out, without retardation effect the current has to be found out here. Okay, and then we have to assume that whatever the distance r is there, it is large compared to the length of the particular dipole, or what you can say, the operating wavelength. Okay, operating wavelength is also very large compared to the length of the L here. Then S is equal to R, you have to neglect whatever the phase differences we are having of from the different parts of the wire here. Then we will be having a smooth angle, sorry, as retarded with scalar potential V of the charge distribution is. We can get the charge distribution here, and then we already know that only there is a charge distribution at the ends of the dipole here. Okay, plus q and a minus q here. We know the relationship between charge and the current here. Substitute in this particular equation and you will have the final answer as ER, E theta and E phi here. So this is the one topic which I want to discuss there in this particular video here. The next topic which I want to discuss is a thin linear antenna and radiation resistance. These two topics I have already discussed in another video here. Let us not go ahead with that one. Now let us consider the thin linear antenna. So this thin linear antenna is nothing but here its diameter is very small compared to the wavelength here. Okay, diameter is very small, that is d is so much less than the lambda divided by 100 here. D is nothing but here diameter of an antenna and lambda is nothing but the wavelength here. Antenna is fed at the center here. We are going to consider that whatever the feeding is there concerned with the antenna, it is been fed at the center here by a balanced two-wire transmission line here. And what we are going to assume here is there are different kinds of current distributions are there here. Okay, triangle current distribution is there. Okay, and the sinusoidal current distribution is there. So we are going to consider the sinusoidal current distribution along the various length of the line here, as shown in the particular figure here. Now, if at all figure shows the symmetric thin linear center fed antenna of length L here, what is exactly the magnitude of this particular current here, which is being flowing in this particular short dipole here. Okay, so now I wanted to understand I is equal to I naught 2 pi by lambda L divided by 2 plus or minus Z here, the equation number 1. Suppose if you are going to consider the retarded current here, then we need to add this e raised to j omega t minus f r divided by c here. Okay, now this particular function is a form factor here for the current on the antenna here. Whenever the Z is less than 0 here, L by 2 plus Z will be considered. If at all Z is greater than 0, L by 2 minus Z is considered here. The total radiation field due to the antenna is obtained by considering the antenna is made up of a series of infinitesimally dipoles of length dz here. Okay, and integrating the field due to elementary dipole over the entire length here. If at all we consider in this case here, so what are the equations of the short dipole here, considering, or you can say thin linear antenna here, considering for the far fields here, if at all it is being center field here. So H5 is equal to J I naught is nothing but here your what is, you can say that retarded current here. Square bracket I naught T is nothing but here it is retarded current divided by 2 pi R here, the cos terms here, and in the denominator we'll have the sine term here. The same the E theta also we can consider 60 into whatever the retarded current is there divided by R, and the cos is the sine terms here. So I naught is nothing but here you can replace with this term here, and E theta is nothing but here 125 into H pi here. Okay, this is how we can explain regarding the thin linear antenna here. Okay, so we end up with this video covering the short electric dipole and the thin linear antenna here. Okay, if you really have any thoughts here, please message me.